Hey guys, welcome back to part 2 of Thinking AI Diabetes Dataset. So if you didn't watch part 1, that was all about me going through the data, learning about it. And this part, we're going to actually dive deep into the machine learning, test out a few models, learn a bit, and it'll be great. So if you guys didn't check out the first video, part 1, I recommend you do so. Link is going to be down in the description so you can watch it and then come back to this one so you can just understand, I guess, more of the deeper understanding of the situation we're modeling around. All right, let's hop right into it. So to start off, machine learning, we always have, or at least this kind of thing, we always have to train test split. So that's with our x variables and then our y variables. So our x variables, that's going to be everything besides this dp value. So x is equal to data frame dot drop dp on the axis of 1. And remember, the axis that we're giving it is telling it, hey, is it a row or is it a column? So by saying, all right, we want to drop something with the index dp, and then we're telling it it's a column, it'll know, all right, cool, that's where it is. Next, we want to actually take this column, because that's our label or response variable. That's what we want to predict. So df dot, just df dp. Cool. Now we have our x and we have our y. Now we have to run the train test split. Training variables and testing variables allows us to efficiently train our model while also getting a good evaluation on how good our model is performing when predicting new values. So what we can do from this is say from sklearn.model selection import train test split. And now we actually have to, again, it's a function, so x train, x test, y train, and y test. You have to make sure it's in this order. Train test split, x, y, right? Because we want to pass in what values, what is their, again, you start with your x value, which is your features, and your y labels, and then the test size, which says, hey, what portion of this total data will I test on? So looking at, we know that our data is 442 pieces long. I think maybe just 20% might be a good number to be around just for this case. So we have, I guess, a lot of data to, we'll have around 354 data points to train on, and then around 89, 88 to test on. So I think that's a good number. So I think 0.2. And then I also just like to do this when I like to create a random state. So what a random state does, it's a variable you give it. And so every time I give it that 101, it'll have the same train test split. This allows it so my run through every time can be the same. Alright. Next. Let us start off. The one thing we noticed from our, I guess, understanding of this data set, that we should try out linear regression. So just say that linear regression. All right. So from sklearn.linear_model, we want to import linear regression, of course. And this is one of the simpler ones, so you can just create the model. Actually, we'll call it linear model, just because we're gonna have multiple types of models. It's good to have your variable names good. So again, just to give a basis, linear regression is just a straight up line of best fit, and is linear, it has to be a straight line. So it just finds which straight line, just, I guess, line of best fit to get most of the data. So linear model, and then I guess reduce the cost function. So linear model dot fit, you want to fit it or train it on some data. So that's our x train, y train. Cool. Now I have this. This is basically the linear model holds the best line almost for that data. linear line, or nearly the best. So then we want to get our predictions. So predictions equal to linear model dot predict x test. Cool. We have our predictions. And then I'll just put that up here. Another thing we have to do is once we have our predictions, we have to see how good it is. We can't do a simple equals to because we want to get the percentage of how much I got right. And it's by just subtracting it doesn't give a really good value. But no, I'll both do, if we were just to subtract the predicted point and the actual point, we'd get something called a residual. And this residual, either we can use something called mean absolute error, which just adds up all the absolute value of all these residuals, and that's your error. Or you can use something called root mean squared error, where it takes all these residuals, squares them, adds them together, and gives you that value, and then you just square or root it yourself. So that's in the same units as your actual data or your actual y value that you're predicting. So we're gonna import both. So from sklearn.metrics, import mean squared, mean absolute error, comma mean squared error. Cool. Oh. 1 second, I have to figure out how to import two functions. Here I'm back. Turns out there was no error. I actually added an S, which screwed everything up. So cool, fun. This. Now I'm gonna print out two values: the mean squared value and the mean absolute error value, and I'll tell you what they mean. So np.square root mean squared error of predictions. Or I think it's y test, and then pred, getting on average 52 away. We'll get back to that. And then mean absolute error of pred, our y test, and our predictions. Alright. The absolute error gives us that on average we're 42 away. The only reason these numbers are different is because of the way they go about figuring out your error. This one squares it, putting much more value to points that are farther away, giving them much more weightage than ones that are close by. And this mean absolute error, just as everything is weighted the same. So here we can see on average we're 52 or 42 units away from this disease progression value. So again, if we look here, this goes from around 25 to 350. If we're on average like 52 away, that is straight. That's like 14% off most of the time, which is not that good, but we'll see. Well, it's yeah. So that's basically what it means. On average, we're 52% off. So that's on average will be 14% off. That just being take this value and divide it by the range of your values. If this range was from like 1 to 1,000, 52 off would be a very good number. But here, it's not that much. You know what? Next thing I want to test out is something called elastic net. Elastic net regression. Alright. So what elastic net regression is better. So elastic net is the combination of two regularization functions, or another two like loss functions, which is lasso regression and ridge regression. So just to put in simple terms, I'll put some links that explain a lot better than I can in the description. Basically, if my linear model predicts that I have all these points here, and my linear model predicts that this is the best line of fit, I can apply elastic net regression that'll slowly, based on the slope of this function, slowly just correct it. It adds some kind of bias. This bias being it adds some kind of loss or error, but it's just a correction of the slope. I think that's the easiest way to say it. Actually, wait, you know what? I'm gonna just clear up. I got my thoughts in order. All right. So elastic net is the combination of two regularization functions, which is lasso regression and ridge regression. These two are used to combat the noise of functions that might not have almost any impact on it, and that just like screw up our data. So if you look here, we can see that sex, we are doing machine learning including sex, which honestly I feel like I should have taken out now, but it's fine. Um, and I don't think it may have something, but I really don't think based on this uh, correlation, it doesn't have much to do with it. So it adds noise to our thing and almost screws it up a little bit. Our function or linear regression. So what ridge regression does is that it adds another variable which basically counteracts this noise. It it's almost like, one second, I'm trying to remember the word. It adds almost this tuning parameter to get rid of that noise. Then lasso regression, on the other hand, which stands for least absolute shrinkage and selection operator, what that does is it takes it and basically moves all of the data down to what really matters and the most important features. So what we'll do now is just elastic net is a combination of the two. It has a ratio of, hey, how much of the ridge regression should we add and how much of the lasso regression should we add, and then another ratio value of how much of this total loss or correction should we input into our final answer. So it'll be a little easier once we start coding it. So from sklearn.linear I want to import elasticnet CV. So if you see here, there's two, elasticnet and elasticnet CV. CV being cross-validation. So by importing elasticnet CV, in a previous video, we used something called grid search CV to test all the combination of values. Now that's built in, because it uses cross-validation to do that. Elasticnet CV is just taking elasticnet and combining grid search CV into one. And it allows us to put, that model itself tests out every type of combination of like parameters, hyperparameters we give it, and gives us the best one back. So here we say I also need to import our import our metrics later. So elastic model, just copy that. Elastic model is equal to elastic net CV L1 ratio. So this L1 ratio is how much ridge regression to lasso regression should we use, right? And L1, what this basically saying is if it's 0%, we use only ridge regression. 100% or 1, we use all lasso regression. So because lasso is a little bit better than ridge, or at least in my opinion, and I guess more people use it, the recommended, I guess, array is 0.1, or just to start is 0.5, 0.7, 0.9, 0.95, 0.99, and 1. Right, this is, I think, right off the documentation. Next, we have something called epsilon, epsilon values, which I'll explain in a bit, 0.01, and then n alphas. which is, I'll say 100. So this epsilon value is almost like the ratio of steps we take in this. Kind of hard to explain this, but what we're basically saying is I want to test on the range from 0 to 100 alphas, or alpha values, which is how the ratio of how much this error affects my actual like slope or final fit. And this epsilon value is almost like a ratio of steps you take in this n alphas, if that makes sense. And then we just have to set max iter to just a large number. This is just how many iterations it does. Just make sure, and then verbose equals 2, just because I want to see some information. Elastic model dot fit is equal to, or model dot fit x train y train. All right, cool. You see, it did out of 100, get 100 steps, and each of these were the alpha value. Or 100 did a lot, I guess. Yeah, so you have the whole path. I'm gonna have to look into that. I'll put some useful links. I really do not know like much about the epsilon and alphas. I'll put some links in the description, and hopefully in the next video or another video I can explain it a lot better than I did now. I'm sorry for that, but I'll make sure to, in the next model, I'll make sure to explain a lot more clearer. So we have elastic model dot L1 ratio wow. And what this does, it says, hey, using a 1L1 ratio, basically saying, hey, Lasso Regression is the way to go. That is the best error, or the best model for you. So next, again, my prediction values. So I'll just do np dot square root mean squared error of y test and predictions, and then mean do that in a different one. Mean absolute error of y test predictions. So weirdly enough, I guess the Lasso Regression didn't do much, meaning even though that sex had such a small value, it was basically fine. It didn't really impact nothing. It didn't impact nothing at all. All right, so let's go into our actual other models, which I am going to try out. K nearest neighbors regression. All right, so K nearest regression. All right, so from sklearn dot neighbors import K neighbors regression. Did I spell neighbors wrong? Neighbors. Import K neighbors regressor. All right, so I'll explain what K nearest regression is a lot better. So let's say we have two or one variable, one x variable, and one y variable. What K nearest regression does is it'll plot the point in the graph, let's say right here. Then it'll find the nearest neighbors towards it. So it says, all right, between this, I have three very close neighbors, these 3 points right here. Right? And based on those 3 points, it averages out and says, all right, my DP value is probably 180, 160, or whatever. And it'll do that in this like 14-dimensional graph that we have, or like 1, 2, 3, 4, 5, 6, 7, 8, 9. In this 9-dimensional graph, it'll plot it, say these are the nearest neighbors towards it, therefore this is my disease progression value, which is a very helpful thing. All right, K nearest regressor. So to do this, what I like to do is I do not use grid search CV. I'll explain why when we plot, but for this one, I'm going to use a for loop. So first, when creating the for loop method, use errors, create your own array of errors. I'm just gonna do, I guess, mean squared error. Actually, I could do both. Yeah, so ms error, and then ma error, right? So next we want to do for n in a range from 1 to 100. I'm going to test out 100 different, or 100 neighbors, because n for neighbors, so model is equal to k neighbors regressor, and neighbors equals n. So yeah, what this does, it says how many neighbors near me should I take a look at? Should I take a look at the nearest neighbor, the 2 nearest neighbors, 3 nearest neighbors, all the way to 100? And it'll test all of them, get the errors, and then what I'll do is once I have these list of errors, I plot them out and I can see them. Let's say, all right, this is the best point to go. And I'll go more into that. So we have our model. Oops. Model dot fit x train, y train, predictions or ms error dot append, actually no, what, preds is equal to model dot predict x test, nah, yeah, x test. Now in the mean squared error, I do np dot square root, mean squared error, my y test, which is my actual values, and then my prediction values. And then that's the same thing for mean absolute error. Just take out the square root and then absolute error. So we can just let that run, and ms error not defined. Oh, cool. So now that trained our model 100 different times, and we got it. Next, it's time to plot our 2 functions. So plt dot plot on the range from 1 to 100 errors or error value. So ms error, we'll do mean squared first. Plt dot x label, just to add some nice looking stuff to ours. Number of estimators, and then plt dot y label is our ms error value. Let me run it. Here we can see that it's between 0 and 20 is when our lowest ms error is. We can do that same thing for the mean absolute error. Okay, cool. Between 0 and 20. They're actually very similar, which is pretty cool. So plt.xlim from 0 to 20. And we can see 10 is where it's at. That's when our mean squared error is the lowest. So plt.xlim, let's do the same thing. 0 to 20. No, 0 to 20. Again, 10 is where it is. So the reason I like to do the graphing method here rather than using grid search is that if you look here, imagine this actually went down at 40, right? So it went here, down, went up, down 40, to the same place it was at 10, and then went back up. Grid search CV might say that the 41 is a lot better. It'll give me the 41 as the best one. However, that literally gives the same error as when it's 10, right? So why use that 30 other estimators, which give me the same error value? It'll take so much harder to fit the model, so much harder to predict, and it just takes it's more labor intensive. So why do that? So just go to the 10. It's faster, less labor intensive, and just easier. As after that point, or between these 2 points, there's not going to be that much of a difference, which is why I like to go the for loop method, just graph it out, and easily save. So now we have this, we can see our mean squared error, and then in the 9th spot, and then our, just to double check, yep, in the 9, and then our mean absolute error, So again, 40 and 52, which are better than the other ones. And honestly, yeah, I think, yeah, it's a lot better than the other one. So we can see here now that K nearest neighbor is our best function. And I think that I'll go with these three machine learning models, just to go a quick overview of them. Linear regression, just straight up line of best fit. Now there's a different part of linear regression, which is elastic net regression, lasso regression, array regression. What these do is they use something called the bias variance trade-off, where they add more error, but they less variance. So it's more towards the trend of the data. It fits the trend better. It adds more loss, but makes the trend better. And it counteracts this noise that is created from these variables that are not adding anything, and they're just there to screw us up a little bit. The ones that not really used for machine learning, they're not should not be used for machine learning model. Next, we have K nearest regressor. Let's actually test one thing. What if I remove 6? So, because that was something I realized might not actually do. 6. Will you do it? And then you can put in a array. So again, I think these values are around the same. Elastic net, they'll be like the exact same as the other one. Okay, wait, sex actually adds a little bit, but we can see here. 5342. Huh. Okay, that's kind of interesting. So yeah, I guess that's kind of weird. 52.7, 52.7. Oh, So this is one thing we're curious about. Do we take the linear regression because its mean squared error is a little bit better, or do we take the K nearest regression because its mean absolute error is a little bit better? So it's kind of interesting to see. I never really thought of that one before. I'm thinking we go with the mean absolute error in this case, actually, because their mean squared errors are honestly around the same. 0.2, not that much of a difference, especially in this case. Did I square root it, right? Yeah, I did. Yeah, they're not that much in this case, honestly. So I'm thinking, all right, mean absolute error is the way to go. So let's just straight up use that. So we want to now create our final model. All right. Final model creation. And this is always the easiest step. We just say final model is equal to, we have to figure out 10, right? That was our best nearest neighbors. So K neighbors regression and neighbors 10. We tune this hyperparameter successfully, so then we're able to figure out that 10 is our best value. So then dot fit, we fit on all the data, x and y, just so now that this is the best model that it can be when we deploy it. That's why we use a train test. The train test to see how good the model is. But once we figure out what the best model is, we want to just use all the training data we can, honestly. So now we can export slash import our data. We want to import joblib.dump. We want to dump this final model into final diabetes model.pickle. Right, and then joblib.dump our list of, or just let's just do all columns. So list dot x x dot columns plus list dot column as diabetes column names dot pkl. Actually, let me just put this in that data. Let's just data frame. Diabetes data dot pkl. Diabetes data dot pkl, because we did create our thing. All right. Now that we have these two, we can, if we go to our diabetes data, we see diabetes data dot pkl. Oh, we have to take a look at that. Can we load it? Let's check. So joblib dot load. Yeah, I think that's function. Yeah, joblib dot load. Just double check, and that is. Let's just copy that. I'm gonna copy this one. I want to, because with the model we can't really see anything with it unless I have extra data to predict on. Yep, loaded it, and cool. It's got our DP, all our serum values, BP, BMI, age, and sex. That is it for this video. I hope you guys learned. I know I was a little bit bad on explaining the elastic net regression. I'll put a lot of links down below just to help you guys understand. And I hope everything's clear. I'll also put some links about Nearest Regression and maybe linear regression just so you guys can understand more deeply about it. And I'll see you guys in the next video. Bye!